Hello, everyone. Welcome to the fourth Electron Devices and Solid-State Circuits online seminar. Thank you very much for joining us. So this is Shaun from Hong Kong University of Science and Technology. It's my great pleasure to introduce our speaker today. Dr. Xiang received his bachelor degree in physics from Peking University, China, and a PhD degree in electrical and computer engineering from University of California, Los Angeles. Then he moved to Stanford University, where he is now a postdoc. He is an expert in novel materials and devices for non-volatile memory and neuromorphic applications. He is the author of IEEE Industry Roadmap for Devices and Systems. He has published more than 30 papers with more than 1,000 citations. Dr. Ni also has extensive entrepreneurship. He acted as the chief technical officer at Instant, in NSF-funded memory startup. So without further ado, Dr. Ni, please go ahead with your talk.
Thank you, Professor Shaun, for inviting me to give this talk to the students at HUSC and maybe new friends that are interested in my research. So I found that online Zoom talk very informative. It can bring people from around the world to share their thoughts about new research. So just bear with me if you have any because I'm in the US. So, but feel free to interrupt if you have any questions. I aim to make this talk more tailored to junior students, and I do not want to go into too many details. More general discussion. I think be beneficial to all of us. So today I'm mainly talking about the context of magnetic memory for big data intensive applications, how we can use bottleneck approaches to activate of magnetic memory. In particular, I will touch upon three aspects of the memory design. So one is materials, the second is properties, and the third one is the application performance. So I will introduce two frameworks that can bridge these three aspects and bring them together so that we can understand and develop the magnetic memory faster. I'm with both material science and electrical engineering department at Stanford as a postdoc. First, I'll just talk about why we're interested in memory for intelligent electronics. So as we know, the current huge success of AI and machine learning is driven by three main drivers. The first one is that we all know that Moore's law driven by the ever-increasing computing power. So it's doubling the power at the same cost for about 1 to 2 years. This has been happening for the last almost 50 years. So this has given us a really powerful tool to compute and calculate information. And then the second part is that we have a lot of data at hand to for the processor to calculate, right? So this is mainly coming from the data storage and data centers, mainly hard disk drive and solid state memory. So this is also very critical. And the third one is more recent development, is the bio-inspired algorithms. Although it has been around for a while, but because of the existence of very powerful processors and storage device, these algorithms can actually have a really powerful impact. And by leveraging a lot of neural networks or short-term, long-term memory, which has been coming from the biology of human body. So if we consider more, plot the electronics hardware over the years, in terms of their throughput, meaning the giga operations per second. So here is the vertical axis versus the power consumption. So we can see that there's very obvious correlation here. So if you want more powerful computing machines that's higher throughput, you need to put up more power into it. And if we consider the future, trend that's going forward, we'll see that if you want to more powerful machine learning models to process more data, obviously need more throughput and more power. And this is going against the physical limitation. You cannot have a lot of power in a single chip or a workstation. So in that sense, people in the community are thinking, okay, how to tackle this? So one professor at Stanford, Professor Horowitz, he has conducted this study to see what about consumption of all the processor actions that's happening. So we can see here that actually the most power consuming one is the DRAM access, meaning you have to bring data from the main memory to the CPU to process, like add, multiplication, etc. And that energy is actually 3 orders in magnitude higher than all the other, process actions, right? So then this brings us to how we can eliminate this, right? So another look at this is if you put the computer memory in a physical sense, then we see that we need to bring the data from the memory to the on-RAM to here to process. And the problem here is that there's a lot of power and delay going in here because they are separate chip, right? So you have to have a bus in between, which is very slow and consumes a lot of energy. And beyond this, you can invest a new type of on-chip memory, which has much higher density, much higher capacity to hold all the AI training data that you need for your algorithm, right? So if we have, for example, 1 gigabyte, 100 times higher density, then we can alleviate the burden of this transfer greatly. And then thirdly, there's another further development that's happening recently in academia is that people are thinking about more innovative ways of actually merging the memory and logic together, meaning they can be done at the same device, or they can be done very closely to each other. So in this sense, you can see the data communication with the logic operation is closer and it's more and more efficient. So today I'm going to mainly focus on the second approach where we try to find a new type of memory that's on chip and has much higher density than SRAM. But note that it's also important that this memory has same or at least comparable performance as compared with SRAM. Otherwise, it's not worth it. So if we take a look at all the different memory technologies available and also in development here, we can see that from hard disk drive to flash, DRAM, SRAM, and we can plot them in terms of 3 metrics. The first one is the density, the second one is the speed, and the third one is the energy for access the bit or write the bit. So in general, if we go from the storage device, which is very high density as shown here, it suffers a lot from a very low speed and high energy consumption. On the other end, if we look at SRAM, It's completely opposite from the storage. So it has a very low density. The energy and speed are very good. So meaning it's very low energy consumption, very high speed, right? So you have this hierarchy of different memory technologies, which have different properties in terms of speed, density, and energy, and we can arrange them in a way that it's a pyramid. I didn't show that figure here, but it's like you can think of that as a hierarchy, right? So that the purpose of that is to leverage the part of each one. And then if we look at this whole space, then we can see here actually in this corner, we have both very high speed, very low energy, and very high density. And actually what I just mentioned, the high density on-chip memory, that's what we want, right? We want the good performance of SRAM, but very high density. So in that research front, SOT-MRAM is kind of a very recent commercialized product can be potential. And now in the MRAM society, we're also looking at newer versions of MRAM. One is the voltage control magnetoelectric MRAM. The other one is the SOT, spin orbit torque MRAM. And these two options will be also the main topic I will talk about today. So next, I will, after discussing all, why MRAM is very good leading candidate of this on-chip high density memory, we can also look at more detail. Okay, so why I want to talk about like these two frameworks of bridging process, device, and applications. So in this sense, let's start with the process. So I know a lot of you might not be familiar with memory. So I will just talk about some fundamentals here. So for a magnetic memory device, the main material is this multi-layer stack. So it consists of a lot of different layers, but the most important are the three layers here. One is the free layer, which stores the magnetic information, 0 or 1, for readout. And the other one is the MPO barrier, and the third one is the reference layer. So this three layer, we also call it a magnetic junction. And you might wonder, okay, what's the use of all these other layers, right? So they have some, very important functions. For example, this part, the pinning layer has to pin the reference layer, so the reference layer doesn't act as a free layer. Right? So there are a lot of intricate physics involved here, and in the design of it, we have to be very careful that each layer serves its purpose. And the very tricky thing is because they are all stacked together, so each layer will impact the other layers, and then it will impact both device function. So in the designing of MRAM, you have to think about the interplay of all these different layers and what's the impact on the device properties. Right? So next is the device side. So once we have this stack, we can pattern it onto this magnetic junction with the pillar structure, a very small diameter. This one is 16 nanometer. And then people, can connect it from the top and bottom electrically and measure and pass through a right pulse. So the right pulse, depending on the current magnitude and the pulse width, you can write the bit from 0 to 1 or 1 to 0, and then you can write a lot of times to get a switching probability. Okay, the switching probability is very critical to characterize the device. Okay, with that, we can further build a circuit. Okay, so we need an access transistor in connection with the MTJ, so that when you build a memory array, you can select one particular MTJ as you want by this FinFET transistor. Okay, so when seeing this, then we can treat this as a cell, and then you can vary the voltage applied to FinFET, and then you can see here with different right or read pulse width, we can have success or failure. Okay, so this is more like a array level or cell level characterization, and this is more closer to the commercial product. Okay, so this is the general three aspects of MRAM I will talk about. Of course, above the circuit design, there's systems, architecture, and then you have all the application above, right? So today I'm going to focus on these three parts. And the main challenge for MRAM at the present moment is that MRAM is still a pretty new technology. With SOT-MRAM just commercialized in the recent few years. So, and there has been a lot of new research needed to make this a more systematic R&D development process. So the problem we are facing right now is that there is no clear link between the process with the device properties and with the device properties with the circuit design, energy and delay metric. So the key thing here is that need to find a theoretical framework that can help us connect all these three things together so that we can develop the technology much faster. So when I talk about this, you might go to your EE fundamentals, and you can remind yourself what people have done in the CMOS industry, right? In the semiconductor industry. So what people have done there is they can actually use this technology computer-aided design, TCAD approach, to link the process with the device and the circuit in a very simple and can be sort of simulated by the computer automatically. And that can provide you very fast feedback of research and development. Then you can do that, and then with the experiments, you can expedite the whole thing very, very fast. So the key thing here is that people have understood pretty well what silicon technology works and how the electrons move, right? So that's the physics understanding of all the process gives you this link between process and device. And then with all the circuit level modeling, which usually comes from phonological modeling, that also based on physics, then you can link this device and circuit together. So in the end, this has helped the CMOS industry or the processor to achieve the Moore's law for the past 50 years. But right now in the memory industry, memory development cycle is much slower than that of the CMOS, of the Moore's law. Right? So in this talk, I'm trying to say that maybe we can think about ways to invent TCAD approach to expedite the memory research and development, like what TCAD has done for Moore's law. Of course, this is three parts, right? So I'm first going to talk about the first link between the process and the device. So this is work done, published last year, and mainly focusing on the voltage control MRAM. And the second part is the device and the circuit part, right? This part is mainly focused on the spin orbit torque MRAM. So I'll get into the first part now. So as I mentioned a few slides before, if we think about what people usually did in the MRAM materials development, so we have this stack of the MTJ, and what we usually do is to change each layer to another material. Okay, for example, change teflon to tungsten, and then there are other different layers. We can do the same, and also we can do different combinations, right? And that approach is a very typical research approach. And what people come up with this, I summarize this by existing literature. So we can see there's a wide range of different data points here. So for this one is the VCMA coefficient, this one is the PMA. So they are important properties for the MRAM. Okay. So I will not go into the details. And we can also plot them as a function of thermal stress. So why thermal stress is important here is because all the materials, when you anneal them, they will interact with each other, and this thermal stress will enhance the properties of the MTJ. And then, so if we look at this, you find that, well, okay, so you have done this, like this is the green dots is what I did. Okay, you have done this point, and this give you this number, but how is that? Why that happens, right? And how we can use this learnings from all these data points to get better results. So that requires us to have a theoretical explanation of what is going on behind all this. And in reality, many researchers have some partial answers to this. For example, chromium versus iridium, maybe chromium has better lattice match with cobalt iron, so it gives you better properties. But this might not explain all the different data points just by one argument, right? So you have to do a systematic approach and see what's the real cause for the change of properties. So what we did here is we designed a stack with 4 different seed and base layers as shown here, and we can also see this wide range of data points, and we selected 4 devices here. The stack is shown here, and the approach we did is to use very careful analysis of the atomic structure and elemental distribution enabled by EDS and TM. So we use this tool to analyze the stack chemistry very carefully. And with that, we can try to see if we can correlate the properties, the electrical properties shown here with the chemistry. Okay. So one example plot here is, this is the EDS, one of the stack. So you can see as the thickness change, different elements have different concentrations. So what we can do is we can look at this iron layer, so this green peak here, and we can find that there's an overlap of oxygen with this iron layer. And then we can take this overlap as a quantity that we want to study. Okay, so we can do this oxygen overlap with iron for all the 4 different stacks, so the 4 different samples. We can plot that area, okay, as a function of these 4 samples, and we can see here the VCMA coefficient, the black dots, actually the trend follows very well oxygen distribution. Okay, and we can also further break down this oxygen amount into more individual components. So the oxygen that reacts with tantalum, magnesium, cobalt, iron, respectively, and we can further analyze what's the underlying cause. But in general, I would say our observation is that the MgO and tantalum O'Malley oxides overlaps with the bottom iron layer correlate possibly positively with the VCMA coefficient. And similarly, we can also characterize the PMA, so the other parameter I first introduced. So we can see here if we calculate the diffusion of tantalum, which is the seed, into the bottom iron, actually this correlates negatively with PMA very well. Okay, so we can see here that these correlations we found are very informative, and also have to note that we did not find any other correlation with PMA or VCMA. We can also calculate all the other overlaps, but only this correlates well with the electrical properties. That's why I think we say this is a systematic approach that can really tell you what's the cause of the change of the device properties. With this, so we have done this, correlation, right? I just mentioned, but if we step back and think about, okay, so now I know this, right? But in real practical world, we start with the stack. The stack is only the material, the thickness, and the sequence. We do not know what elemental distribution will get, right? We have to understand what's the cost, correlation between this. So actually, it's pretty simple to do that. So we can use rather simple material science theory, formation, and thermal diffusion to explain that. So with that, I'll talk about in this next slide. So with this, then we can close this loop. So we can go from here, the stack design, to the device properties, and then we can do a predict and iterative design process, right? In this case, hopefully we can use this loop to expedite the materials research and development. So talk about the thermal and the enthalpy thermal diffusion. So formation enthalpy means how much energy when two elements combine. So how much energy it leaves out. The more negative it is, the more easier they are to format, a compound or alloy or whatever. So if you look at here, the tantalum and moly are actually much easier to be oxidized, the blue column here, compared with uranium. So with that in mind, we can actually explain how the oxygen amount in the cobalt iron changes. And that change, I'll just talk in a few minutes, we actually exactly follows the data we find earlier. Okay, so I'll go over this very quickly. So in general, when we think about this, we also need to note that the thermal annealing temperature is also changing. Okay? So for these two cases, the first and the second stack, when you anneal at a higher temperature, the oxygen in the MgO will diffuse to all the other metallic layers. So the oxygen into this top boron will increase. Concentration I'll plot here will increase from this one to this one. And the same thing happens for the 3 and 4, the higher temperature. While for bottom layer, it's not that, it's different because we have inserted a moly layer here. So the moly, if you remember, it actually attract the tantalum and moly both attract oxygen, right? So in this case, the main reason of the decrease of oxygen in the cobalt boron is the thickness increase, okay? And this same thing happened for these two cases. And lastly, we have to explain the difference between this 2 and 3. And that is because we swapped the tantalum with iridium. So iridium, if we remember, does not interact with oxygen. So in this case, all the oxygen that was absorbed from to tantalum here will diverge to the top two layers. So that's why you get an increase of cobalt oxygen content in these two cobalt boron layers. So this trend actually, is the same, consistent with what we observed in the experiment. So now I have, rather simply explained that we can use this stack design, and we just use this simple formation enthalpy and thermal diffusion argument to say that we can predict how the element distribution change, and then with the correlation we find earlier, we can predict how the device properties will change, right? So with this in mind, we can actually modify the whole stack, and we can introduce additional layers, molybdenum and magnesium here. So they can introduce more metal oxides, which when overlapping with the cobalt iron will give you higher VCMA. And also with the introduction of these two layers, we further block the diffusion of iridium into the cobalt boron layers. That gives you a higher PMA. And that's also what we see in the final device. So this illustrates that this simple approach can actually help us to improve the device properties. Okay. So there's a caveat here that this is still a very qualitative approach. It's not quantitative at all yet. If we want it to be quantitative, we need to do a more careful simulation, Monte Carlo, whatever, to carefully see how the atoms change, diffuse when you have different thermal annealing temperature, different thickness of each layer, and then with that, coupled with the correlation, we find we can have a better, more accurate prediction. Okay, so this is just the beginning, of the more quantitative, analysis or a prediction of the membrane development. Okay, so this is the first part of the two approach, and the second part is more on the topic of spin orbit torque. And this one is more focused on the link between the device electrical properties and the circuit design. But still, this is very, very relevant in terms of material. And we will discuss the materials requirement required by the circuit energy and delay goals here. But more or less, I'm not going to touch upon the correlation between this two in this part, this two part. So you will see that in a minute. So the reason I try to do this part is because SOT, as you might know, is a relatively new field for MRAM research, and there also, as the material scientists and physicists start to focus on this field, the main thing we find is that there are a lot of different materials people. Okay, you have very different SOT efficiency, which is the right efficiency here. And then with different efficiency, the higher efficiency, you have a lower power consumption. Right? And then again, there are a large variation of different properties for different materials. And also, another thing is when you change the thickness of the SOT material, you actually get different SOT efficiency. So when a circuit designer looks at this thing, they'll think, wow, this is really complicated, right? And in their space, in their world, only the energy and delay matters for the circuit to operate, for memory to read and write. So how can we link this circuit level requirements with the device properties and material properties is the goal here. So in this one, we propose this two transistor, one magnetic top junction modeling framework. The main purpose here is that SOT is very different from STT and this voltage control because it's a 3-terminal device. We need to pass a current along this bottom SOT channel to write. And also we need another separate transistor to read it. So there are 2 transistors in this case. And you have to, I saw there's some, yeah, and you have to note that there are several things you need to be careful about. So the first one is when you look at this region, so the SOT layer and the free layer, the cobalt brown, which stores the information, when current flows through it, there's a current shunting. So the current will diverge into 2 layers and then it will go back together at the end. This is one thing we need to be careful about. The other thing is if we look at the dimension from the top, then we can see you have a different physical design that you can play with. And this is the design assumption we use. And then the other thing is because there is transistor involved in the writing process, when you think about it, when we want to write the SOT, you have two directions of the SOT write. So one direction in the other direction. And actually, one direction is stronger, meaning the transistor can provide more current than the other one. This is mainly because in this case, the VGS gate source voltage is close to VDE. In this case, it's smaller than that because you have a large parasitic SOT line here in the right path. Okay, so if we also consider this, we in the subsequent analysis will only focus on the weak path because this is the limiting factor of the right performance. So with that, we can I use this cadence to model this cell, and we can see here that for the strong path and weak path, we do see that the current drive in the strong path is much larger than the weak path. If we plot it in terms of the resistance, it's also consistent. And another thing is, if we increase the SOT resistance, okay, then we can see here the current drive that the transistor can provide actually decrease pretty fast. That's like a parasitic, right? If you have a large parasitic, then you have lower transistor drive. And this is pretty serious issue. If you have very large resistance like 10 kilo ohm, then in this case, the current drive in this scenario is almost half of the original maximum amount. And also another thing is, if we look at the actual layout that I assume, when you calculate, for example, for a tungsten SOT line, the resistance is actually about 1 kilo. So it's sort of on the same order as the SOT line resistance, as the transistor resistance here, 5 kilo, 10 kilo ohm, but it's usually much smaller than the transistor resistance. Okay, so that's another very critical thing we have to be very careful about when you analyze the circuit level performance. Okay, so now I will switch to this link, the model that we construct. So this is pretty well known in the field, so I'll go over very quickly. But the basic idea is we can model switching current or the right current using this theoretical equation, and then we can take into account of the shunting current, and then we can also take into account the physical layout to get two things. So one is a switching current, the other one is a switching energy. Okay, and very interestingly, because we want to see what parameters in this model will actually we can control and optimize for better circuit level performance, right? So we can actually only use two parameters that we think are most important here. So one is the spin hole conductivity, the other one is sheet resistance of the SOT material. Okay, and all the other parameters are either for the free layer or something that we think can be optimized to be a relatively constant value. Okay, there's a lot of simplification here, but I'll show you that what we can get from the simplified picture. So with these two parameters, I also want to mention that we assume they're independent of each other. Okay, this is relatively sophisticated physics here, but I'll just leave it here for anyone who are familiar with. In this clean regime, we can assume that the sheet spin hole conductivity is relatively constant when you change the sheet resistance. Okay. So let's just assume that. And if that's the case, then we can write the switching current and switching energy using this very simple, simplified equation here. And the one thing that I used as an assumption is that the total FinFET resistance is much larger than the SOT resistance, which I will confirm later that this is the case. It is true in all cases. So if it's in this case, actually the energy and the current, when you want to optimize it, it's the same thing because the energy is proportional to the square of the current times the FinFET resistance. Okay, so in this case, we can use and plot this figure. So this figure tells us that the switching current is a function of the sheet resistance. So when you have a larger sheet resistance, you have a lower switching current by this equation. And also when you have a higher spin hole conductivity, this parameter here, you also have a lower switching current. Okay, so this is pretty reasonable in the physics picture. However, there's one caveat I also mentioned earlier a little bit, is when you have a very large sheet resistance, you will have a very large SOT line resistance, which is a parasitic in your cell. So if that's the case, if it's too large, then your current drive from your transistor will decrease pretty fast. So when it's very large, larger than 2000, actually all the switching current decrease, but the transistor drive, meaning the current that the transistor can provide, actually drop even faster. And in that case, you need more fins or a larger transistor to do this, right? So you're sacrificing energy with density. And this is a trade-off we need to think about. But overall, I would say what we want is a larger spin conductivity and moderate sheet resistance. Okay, so it cannot be too large, and also it cannot be too small. So when the sheet resistance is very small, the problem is you need to pass a lot of current because it's too conductive. So you need to pass a lot of current, then you need a larger transistor as well. Okay. So there's optimal range here. And then in the end, we also can model that if we change the thickness and the resistivity of the SOT material rather independently, we can see that, for example, in the tungsten case, you can have different spin hole angle, right? That depends on the spin diffusion in this case. But if we can do this two-dimensional modeling, then we can find that actually in this region that we can have the smallest fin number, 2 fin numbers, then you can do this 0.5 nanosecond switching. Okay, the current here is around 110 microampere, and the energy that's consumed in the FinFET is about 50 femtojoule. And also we can model the energy consumed in the SOT line. Okay, so in this SOT line, actually the energy consumed is much smaller. This is because the resistance of the SOT line is much smaller than the transistor shown here. Okay, this also confirms my previous assumption that we only focus on the FinFET energy rather than the SOT energy. Of course, you can change your circuit design or layout and your thickness of your material so that you can maybe have a more resistive SOT line. But then in that case, you have also a trade-off. You will also increase this, right? So at the end of the day, this is a complex issue, and then you have to think about the whole all the different components together. So I just want to conclude here. I first discussed why MRAM has some great promise for high density on-chip cache, and then I discussed briefly how to propose a predictive and iterative materials design framework in the context of voltage control, MRAM. And lastly, I introduced this SOT-MRAM model that can tell us what kind of materials, what spin hole conductivity and sheet resistance are needed to enable high-speed, low-power operation. And at the end, I want to say that maybe this two framework can help us to achieve a new paradigm of MRAM design using a TCAD approach, which will be much faster and will help MRAM and other memory technologies to catch up with CMOS and deliver the potential of them. So lastly, I want to acknowledge the funding agencies from both my PhD at UCLA as well as Stanford. And I will be happy to take any questions. Thank you.
Thank you, Dr. Ni.